we looked at finding areas of unusual shapes, but we can also use integration to find volumes of unusual shapes. And we're going to focus on ones here with just circular cross sections. And later in extension 2, we'll see how to deal with other sorts of shapes. So, random curve. If I was to take the curve from A to B, and then rotate it, ooh, there we go. We end up with some sort of a vase or something, put flowers into. Well, it's fancy, the things that your mothers think are wonderful, and you look at it and go, it's one of those things. Okay. How do we find the volume of such a thing? Well, you remember when we were doing area, we split it up into rectangles and summed all the rectangles. We can do a similar sort of thing. We could sum all these, well, they'd be cylinders, and hopefully the height of the cylinder would be as close to 0 as possible. So, but we could sum all those up and get the actual volume. Now, in extension 2, as I say, we'll go into a lot more detail how we create that. But for 2 unit, and 3 unit for that matter, it's good enough we can just quote this formula. So it turns out the volume, pi times the integral of y squared dx. That is, of course, if we're going around the x-axis. And if you look at it, it's the area of a circle. It's pi r squared. The radius of the circle would be the y value. And so we're just summing up all of those from A to B. If we were going around the y-axis, then it would be x squared dy. That's say 2 unit, 3 unit, we can just quote that and everything's fine. Extension 2 will end up deriving it from first principles. So let's now create some formula for shapes that we actually know. If I was going to rotate y equals mx around the x-axis, I would get a cone. So I'll call the x value conveniently h, because that'll turn out to be the height of the cone. Rotate around, and there it is. So there's the cone. So I'm going to integrate, we're going around the x-axis, so it's y squared dx. Well, y is mx, so I'm going to integrate m squared x squared. M squared is just a constant, so I could pull that out the front. And integrate the x squared, 1/3 x cubed, substitute in h, substitute in 0, and there's the formula for the volume of a cone. 1/3 pi m squared h cubed. I'm sure you recognise it. The reason it looks different, of course, is it's not in terms of the radius, it's in terms of the slope of the cone. So let's substitute in radius for slope. Let's come up with that. Well, the radius, so r over h would be the slope. I could substitute that in, and sure enough, there we go, 1/3 pi r squared h. It does come out. Let's do a sphere. So if I get a circle and rotate it, obviously I'm going to get my sphere. Whoop. There we go. Now that looks like a sphere. Okay, we're going to go y squared dx. I suppose I could have just easily gone around the y-axis as well. It's a nice symmetric shape. Well, x squared plus y squared is r squared, so I can rearrange that and get y squared, the subject, straight away. So we're just going to integrate r squared minus x squared. I'm going to take advantage of the symmetry and say it's twice from 0 to r. Okay, so r squared x minus 1/3 x cubed. Substitute in r, and this one drops out a lot nicer than the cone. There we go, we get our 4/3 pi r cubed. See? It does come from something. We didn't just make these formulas up. We're going to rotate the parabola, y equals x squared, around the y-axis, going from 0 to 1. So there's our parabola. We're going to go from 0 to 1, rotate it, and the shape we get is a paraboloid. We're going around the y-axis. So x squared, well, we've already got x squared, the subject here. X squared is equal to y. We're going to integrate y to y. All right, add 1 to the power over the power. Substitute in, oh, we got pi on 2 units cubed for that one. The actual integrations don't turn out to be too bad usually. The shaded region is rotated about the x-axis. So we're going to end up with, well, what's it going to be?
It's like an amphitheatre.
A which? Oh yeah, I got you, mate. Yeah, because so like the seating sort of goes up like that, yeah. All right, well let's do it. Pi times integral. But remember, just like yesterday with area, when it's between two curves, which technically is what we've got here, because we're doing the area between the horizontal line and the and y equals 5x, top minus bottom. But you square it before you subtract, because you're basically saying it's the volume of the top one minus the volume of the bottom one. So over here, it's 5 squared minus 5x all squared. So 25 minus 25x squared. And subbing in 1, subbing in 0, there's our answer. But of course, that would not be the best way of doing it. Because just like I said with area, when we've got a formula that already that does the job, it's quicker to do that. What we're basically talking about here, if I rotate that horizontal line, I'm going to get a cylinder. If I rotate this angled line, I get a cone. So it's pi r squared h minus a third pi r squared h. 2/3 pi r squared h. The radius is 5. The height is 1. There's our answer, 50 pi and 3. HSC question. So we've got a parabola and an upside down parabola. Find the points of intersection of the two curves. All right, well, we've got to solve them simultaneously. So x squared is equal to 12 minus 2x squared, plus or minus 2. Okay, so we've got our... Oh, but it says the points, not just the x values. So subbing back in, we know they meet at 2, 4. Oops, I should have said minus 2, 4 as well, shouldn't I? Because it does say points. Now, that shaded region, rotate around the y-axis. They're giving us a hint by splitting the region into two parts, or otherwise. So if we're going around the y-axis, again, we've got boundary problems. We start at 0, and it's the concave up parabola to the y-axis. But as soon as we go past the point of intersection, it then becomes the concave down parabola. So splitting it up into two volumes, add them together. So our boundaries change. But it does say or otherwise. I wonder what otherwise would be. But anyway, okay. So pi, we're going around the y-axis this time, or more correctly I should say, going around the y-axis. I'm going to have to make x squared the subject. The concave up parabola already has x squared as a subject, so x squared is y. The concave down one, when I rearrange that, x squared is 6 minus half y. So adding these two together. Now I can't combine these integrals, I've got different limits, so I have to just treat them as different ones. Add around the power over power, substitute in, a bit more calculation, we get 84 pi units cubed.